Light interacts differently with different materials. It is either absorbed, reflected, transmitted, or refracted. Today we are going to be looking at reflection and refraction. Here is the DSF STEM light kit that will help us understand reflection and refraction of light better. Let us start off with laws of reflection. We already knew that the first law states that the incident ray, the reflected ray and the normal ray at the point of incidence lie in the same plane. And the second law states that the angle of incidence is equal to the angle of reflection. We are going to look at the second law in a bit more detail by doing an activity. Here are the materials that you require to do this activity. The ray of incidence is marked with the help of two pins, and you can also see the normal in red here. Also observe that the reflecting surface, which is a plane mirror, is exactly perpendicular to the normal. To complete this activity, you would have to place two more thumb pins in a way wherein it is aligned with the reflection of the pins that is obtained. Once we do so, what we can do is remove the pins, join and form a line using the positions of these two pins that we just placed. Once that is done, we can measure the angle of reflection. Then you will be able to see that angle of incidence, which was 45, is exactly equal to the angle of reflection, which is also 45 degrees out here. You can try this activity with different angles and you would get the same result. Keep in mind that the angle of incidence and reflection are found with respect to the normal. Now let us look at the image formed in a plane mirror. Observe what is happening to the image when you are moving the object. You will be able to observe the image is as far behind the mirror as the object is in front of it. The image is as big as the object, and that the image is laterally inverted. Now let us look at the characteristics of an image. An image can be real or virtual. An image is called a real image when the rays of light actually meet at a point to form an image, and it can be caught on a screen. In case of a virtual image, the rays of light don't actually meet, and hence such an image cannot be caught on a screen. If the placement of the image is exactly as that of an object, it is called as an erect image. If the placement of the image is upside down when compared to the object, it is called as an inverted image. If the size of the image is larger than that of the object, it is termed as a magnified image. If the size of an image is smaller than that of an object, it is termed as a diminished image. Now let us look at spherical mirrors. Spherical mirror is a section of a sphere. It may be concave or convex. If the reflecting surface is the outer side of the sphere, we call it as convex. If at all it is the inner side of the sphere, we call it as concave mirror. Let us try to understand certain terms with regard to concave and convex mirrors. We can see that the mirror is part of the hollow sphere, right? Hence, the center of the sphere is the center of curvature, and it is represented by the letter C. The radius of the hollow sphere, which the mirror, center of the spherical mirror, is called the pole. A straight horizontal line passing through a pole and the center of curvature is termed as principal axis. Principal focus for a concave mirror is the point at which rays parallel to principal axis coming from infinity converge after being reflected by the concave mirror. The principal focus for a convex mirror is the point at which rays parallel to principal axis coming from infinity appear to converge after being reflected from convex mirror. The distance between pole and principal focus is termed as focal length. It is represented by the letter F. Always remember that the focal length is half of the radius of curvature. Always remember that a ray of light which is parallel to the principal axis will have to go through the principal focus, or at least appears to go through the principal focus. And any ray which goes through the principal focus has to come out parallel to the principal axis after reflection. And any ray passing through the center of curvature or aimed at the center of curvature will retrace its path. Now let us look at the image formation in concave mirror. Materials required for activity 3 are as follows. The setup for the experiment can be seen out here. Let's see what will happen if the object is placed at infinity. As the rays from the object that is placed at infinity can be parallel to the principal axis, it will all meet at the focus. Hence, the image is formed at the focus. Now let us look at the nature of the image. The image is real, inverted, and diminished. Now let us look at an object which is placed beyond C. As you can see here, the rays after reflection meet between C and F. So the image is formed between C and F. Now let us look at the nature of the image. The image is real, inverted, and diminished. What would happen if we place the object at C? As you can see here, the image is formed at C itself. Let's look at the nature of the image. The image is real because we are able to catch it on a screen. It's inverted and is of the same size. When we place the object between C and F, the image is formed beyond C. The image is real, inverted, and magnified. When we place the object at F, the rays which are reflected come out parallel to each other. Hence, they meet at infinity. Therefore, the image is formed at infinity too. Hence, it is difficult to catch it. The image is real, inverted and highly magnified. When the object is in between the focus and pole of a concave mirror, as you can see here, the reflected rays appear to meet and don't actually meet. Hence, the image formed is a virtual image. It is erect and is magnified. Because it is a virtual image, it cannot be caught on a screen. The big blob formed out here is more of a reflection on the paper rather than an image formed because the light rays are not actually meeting. When it comes to convex mirror, the image formation is something like this. If the object is placed at infinity, as you know, all the light rays coming from the object will be parallel to the principal axis. Hence, after reflection, they'll diverge. So they appear to meet at the focus. As you already know, when two rays appear to meet at a point, they form virtual image. As you can see, the image is formed at the focus. It is highly diminished and it is virtual and erect. If the object is in between infinity and the pole, the image is formed between P and F behind the mirror, indicating that it is a virtual image again. In here, the size is diminished, the image is virtual and erect. Now it's time to look at the lenses. If mirrors were just part of a sphere, lenses are a combination of two spheres. If a lens has both the surfaces bulged, it is called as biconvex lens. But if a lens has caved-in surfaces on both sides, it is termed as biconvex lens. Because a lens is a combination of two spheres, it obviously has two center of curvatures, two poles, and two principal foci. And the exact center of a lens is termed as optic center. Always remember that a ray of light which is parallel to the principal axis will have to go through the principal focus, or at least appears to go through the principal focus. And any ray which goes through the principal focus has to come out parallel to the principal axis. And any ray passing through the optic center will move forward without deviating from its path. Materials required for activity are as follows. The setup for the experiment can be seen out here. Now let us look at the image formation in biconvex lens. When the object is placed at infinity, the image is formed at f2. The image formed for the object placed at infinity is highly diminished, real, and inverted. When the object is kept beyond C1, the image is formed between f2 and c2. The image formed for an object beyond c1 is real, inverted, and diminished. When the object is at c1, the image is formed at c2. The image formed for an object at c1 is exactly same size as the object. It is real and inverted. When the object is placed between C1 and F1, you can see that the image is formed beyond C2. The image formed for an object placed between f1 and c1 is magnified, real, and inverted. When the object is at f1, the rays refracted are parallel to each other, hence meet at infinity. So therefore, the image is formed at infinity. The image formed for an object at f1 is highly magnified, real, and inverted. When the object is between f1 and O, the refracted rays appear to meet beyond C1. When the object is placed between f1 and O, the rays refracted won't meet, but they appear to meet beyond C1. Hence, the image formed is virtual. The image formed for an object placed between f1 and O is virtual, erect, and magnified. The big blob formed out here is more of a refracted rays on the paper rather than an image formed, because the light rays are not actually meeting. When it comes to biconcave lens, when the object is at infinity, the refracted rays appear to meet at the focus. Hence, the image is said to be virtual, diminished, and erect. When an object is placed anywhere between infinity and O, rays appear to meet in between f1 and O. The image formed is diminished, virtual, and erect. Let's see what we learned in this particular video. We learned about loss of reflection. We learned about image formation in a plane mirror. We saw how image is formed in spherical mirrors like convex and concave, and we also had a look at the image formation in lenses like biconvex and biconcave.